All right. Very good. Well, hello everyone, and welcome to Phases of the Sun, a guide to our star and the 2024 total solar eclipse. We are thrilled to have all of you with us from all across the country as we prepare for the phenomenon that is the total solar eclipse of 2024. My name is Lynn Barker, and I'm an Associate Director of Alumni Engagement at the University of Iowa Center for Advancement, and I am privileged to serve as your moderator for this evening. So I will be welcoming us and getting us all situated for our hour together. I will be learning along with all of you, and then I will be wrapping us up at the end of the hour. As most of us are comfortable these days in this virtual setting, please know that all participant videos are off and microphones are muted, but we certainly welcome your questions as they are able to be submitted through the Q&A function within your webinar screen. We will save time at the end for questions to be addressed. So if any questions do arise throughout the time together, please don't hesitate to submit those. With housekeeping handled, I'm excited to introduce Dr. Caroline Roberts, who is the Van Allen Observatory's manager and astronomy laboratory coordinator here at the University of Iowa Department of Physics and Astronomy. A mouthful, Caroline. Caroline is our subject matter expert and is here to teach us all about the sun, what powers it, how it moves energy to us on Earth, as well as its structure and features that can be observed. Caroline will also cover solar eclipses, including what they are, what causes them, and tips for safely enjoying the April 8th eclipse. With that being said, I know Caroline has so much to share with all of us with several guest demonstrations. So without further ado, Caroline, I turn it over to you. The floor is yours.
Thank you so much, Lynn, for such a wonderful and kind introduction. Welcome everyone tonight. It's so good to be with you all. So my name is Dr. Caroline Anna Roberts, and as Lynn shared, here at the University of Iowa, I work with our undergraduate astronomy labs, as well as our Van Allen Observatory on the roof of Van Allen Hall. Here I am with a graduate student TA, as well as a student in one of our undergraduate courses. And this is one of my favorite places to be on campus, in our campus observatory, the Van Allen Observatory. I want to introduce a couple other folks who are helping me here tonight. Mary Haig is an undergraduate physics and astronomy major, and Abby Church is an undergraduate pre-business major. They're going to be joining us in just a bit to help us understand a little bit better how the sun works. So first, we will quickly say, what causes a solar eclipse? Well, simply this is, whether it's a solar eclipse or a lunar eclipse, an alignment of the sun, the moon, and the earth. For a solar eclipse specifically, though, this is when the moon passes between the sun and the earth, and the shadow of the moon, every moon in our solar system, every planet in our solar system is constantly casting a shadow back behind it. As the sun shines on it, it sends a shadow back into space. But in this solar eclipse, the shadow of the moon falls entirely or partially on the earth. And we have a great solar eclipse coming up. Here we see a map of the path of totality there in red. We also see different areas of the United States. The numbers represent what portion of the sun will be covered by the moon, how much of the shadow of the moon are they going to be in at different locations here in the continental United States. Everyone in the continental United States, so the United States except for Alaska and Hawaii, will be able to see the sun be blocked by the moon, as many of you know, some of you being in the path of totality as well. And so I want to first learn a little bit about you all and, what is your upcoming role in this eclipse? I'd be curious, please let me know, are you in the path of totality? Are you going to experience a partial solar eclipse? or perhaps you're somewhere on Earth where it won't be possible to see the moon blocking the sun. There will be plenty of people on April 8th who aren't in the path of the moon's shadow. So fill this out. We'll finish it up in just a couple seconds. And I would say vote, where you'll be on April 8th. Maybe you are going to experience a partial solar eclipse in your hometown, but you're planning to travel to the path of totality. It's up to you, but I would say vote total solar eclipse if that's your situation. And I'll see the results now. We can all see what everyone voted. Cool, fantastic. And everyone will get to experience it in some way as long as it's not cloudy, which is fantastic to hear. So as we said, the moon is casting a shadow out back behind it, and sometimes that shadow can fall on the Earth, creating a total or partial solar eclipse. The reason why we have this unique shadow pattern that doesn't have sharp lines is because the sun is not just a single bright source, a point of light. It's an extended source. It's this big ball of sunlight. And so it's going to cast shadows that have this peculiar appearance where in the center, it's dark, this umbra pattern. And around that dark umbra, there's still a shadow that's fainter and hazier. We call this the penumbra. And it's also important to keep in mind that the distance between the Earth and the moon is tremendous. A lot of the models, pictures that we'll look at tonight don't really capture this correctly, but the Earth is very separated from the moon. This is to scale. And so perhaps we could imagine that the sun is way over far on the right here. And so the moon is casting a shadow back behind it. And that teeny tiny thin shadow of the moon needs to fall on the target of the Earth way back here. And getting all of the positioning right so that that happens, you can start to understand that it's a bit rare that that little moon shadow is going to be able to fall on the Earth. It's a little bit easier to understand once you remember how far separated things are in space. But in particular, a solar eclipse occurs when the moon is between the sun and the Earth. There's a line that goes from the sun to the moon to the Earth. And you might think, okay, well, the moon goes around the Earth, and it takes about a month for it to do that. And it takes about 12 months for our Earth to go around the sun once, 1 year. So perhaps there might be an eclipse every month, every time the sun and the moon and the Earth line up in a nice straight line. That would happen in January, that would happen in February, that would happen in March, and so on. And that's sort of true. But one important thing to think about is that as the Earth goes around the sun, it travels in an oval, a nice flat oval. Think of it maybe as like a pancake that it's traveling along the edge of. And as the moon goes around the Earth, it also travels in an oval. It travels around its own little pancake. But the problem is there's a tilt between, we'll come back to this. There's a tilt between the pancake of the moon's path around the Earth and the Earth's path around the sun. The planes of their orbits are skewed off slightly. So we'll hold that thought and just one more time say, the moon casts a shadow with this dark umbra and this dimmer but still shadowed penumbra. If on Earth you happen to be in the umbral shadow, in the darkest portion of the moon's shadow, you will see a total solar eclipse. And so at first, you'll kind of see what partial solar eclipse people see, the moon moving in front of the sun. But there will come a moment when the moon completely blocks the sun. And that moment, you see the outer atmosphere of the sun, and it's really a tremendous moment. If you are in the penumbral shadow of the earth, the penumbral shadow of the moon, you do still see the sun blocked by the moon, but it never completely covers it up. One thing that we'll say a little bit more about in a moment is eclipses are not rare. Things in space are always blocking other things in space. But what's quite cool is that our sun is about 400 times bigger than our moon, but it's also about 400 times further away than our moon. And because of that, there's this nice happy coincidence where the shape of the moon in the sky looks just like the shape of the sun in the sky. And that allows us to have the possibility of a total eclipse where the entire sun is blocked perfectly. And the only thing we can see is this outer atmosphere. Then, of course, there are plenty of places on Earth on April 8th that will not see any eclipse, total or partial, if the moon's shadow does not fall on their location. Okay, but going back to the pancakes, we can think about a time like this. It is possible for the shadow of the moon to fall on the Earth. But if we wait for a few months, a month and a half, as the Earth continues to go in its orbit around the sun, we now have a position where this tilted pancake is not going to allow the sun, the moon, and the Earth to line up perfectly. Yes, the moon's between the sun and the Earth, but you can see it's kind of a zigzaggy line that connects them. It's not a perfectly straight line. And so the shadow of the moon cannot fall on the Earth's surface at this time of year, 3 months later from when we experienced that last eclipse we saw. Similarly, half a month later, the moon is directly behind the Earth, but it's kind of up above now. It's not directly behind the Earth. It's not in the Earth's shadow or anything. It's a little bit too high. So to explain this again, I will show that, we have a couple times a year. Here's our sun, here's our Earth. The Earth goes around the sun over the course of 365 days. Here's the moon. The moon goes around the Earth over the course of 30 days. And so 2 times a year, when the Earth is here and when the Earth is here, we have a perfect alignment: sun, moon, Earth, sun, moon, Earth. And that shadow is capable of falling in part or in whole on the Earth's surface. But the moon, as it goes around the Earth, it has that tilt, that 5-degree tilt. And so it's not matching up perfectly with the pancake of the Earth's orbit around the sun. So if we wait 3 months, we have that problem we were talking about before. The moon goes around the Earth and it's in between, directly in between the sun and the Earth, but the moon's up too high. It's really not in a straight line with the Earth anymore. That shadow can't fall on the Earth. Over here, the moon is too low. We can't have an eclipse at this time of year either. And so even though the moon is in the right position for an eclipse once every month, it's not really in the right position. Sometimes it's too low, sometimes it's too high. And as a result, there's really only maybe 2 times a year that we might even have an eclipse. And a lot of the times, those are just partial eclipses. It's just the penumbra, the faint shadow of the moon falling on the Earth. And we really need to wait every once a year or once every 2 years for there to be a total solar eclipse somewhere on the Earth. So to recap all of that a little bit more, we're going to say a bit about
A solar
eclipses in
eclipse
this video.
happens when a new moon moves between the Earth and the sun, blocking some or all of the sun's rays from reaching the Earth. By cosmic chance, even though the sun is 400 times wider than the moon, it's also 400 times farther away. Therefore, the two objects appear the same size in our sky. Astronomers are able to predict eclipses because the Earth and Moon have very predictable orbits. Why then isn't there an eclipse every month? The Moon's orbit is usually tilted a few degrees north or south in relation to the Earth. When the Moon does eclipse the Sun, it casts two types of shadows on Earth: a smaller, darker shadow known as the umbra, and a larger shadow known as the penumbra. There are four types of solar eclipses. The first and most spectacular is a total eclipse, when the moon completely covers the sun's surface. A total eclipse can only be seen if you're standing within the umbral shadow. That's why the imaginary line created by this shadow as it races across Earth is known as the path of totality. People within the penumbral shadow see only a partial eclipse, the second type. From this view, outside the path of totality, the moon passes in front of the sun off center, never fully covering its surface.
So just a fun little comic here. We can kind of think about some astronomical things that you've perhaps heard of. Certainly our partial solar eclipse, our lunar eclipse, the supermoon, planetary conjunction. Some of these sound pretty cool, but when you see them in person, they're not always too exciting. But a total solar eclipse, that sounds amazing and it looks amazing. And I'm just so excited to share a little bit more about total and partial. It's getting up there compared to the other ones. Share more about you with them. Share more with you about them tonight. I do want to say detail about our title of our talk tonight. We are talking about phases of the sun, which is not really a proper astronomical term. We don't in astronomy think of the sun as going through phases in the same way that the moon does. The moon goes through phases because half of the moon is always reflecting sunlight brightly, and half of the moon is always in shadow. But as it goes around the Earth, we see different fractions of that reflected sunlight and that dark shadow as the moon orbits around the Earth. And so these phases of the moon are a real concept that astronomers talk a lot about and think a lot about. Again, thinking about phases of the moon being caused by, here's the position of the sun. It shines on the moon, no matter where it is in its orbit around the Earth. But we on Earth see different fractions of the illuminated moon and the shadowed moon as the moon progresses in its orbit. So this is the positions, but this is what we see. This is the position of the Earth and the moon relative to the sun over here. When it's at this position, this is what we see. But of course, phases of the sun, we're not looking at any reflected sunlight. We're just looking at the sun itself. And we're not looking at, the shadowed part of the moon at the same time as we're looking at the reflected part of the moon. We are just looking at the shadowed part of the moon. That's the new moon phase. None of the reflected sunlight is visible. Only the shadowed part of the moon is visible. And even the shapes of the phases of the sun don't really look that much like the shapes of the phases of the moon. You can maybe sort of see like a crescent sun right there. But right there, that sun, the moon never looks like that. So a creative name for our talk tonight, but remember that an eclipse is the sun being blocked by the moon. When you think of the phases of the moon, there's no blocking occurring when our moon goes through its phases. We're just seeing reflected sunlight and the portion of the moon in shadow at the same time. Nothing's blocking anything else, like in partial or total solar eclipse. We're going to briefly step away from eclipses for a little while and learn to understand the sun itself better, thinking about what powers the sun. It gives us sunlight, warmth, energy. What makes that possible? And how does that sunlight and energy reach us? How does it escape the sun? In the very center of the sun, this layer that we call the core, gravity is so great that protons of hydrogen, protons are charged positive particles in atoms, and an atom with just one proton is named hydrogen. Protons and hydrogen atoms, four of them get smushed together under tremendous gravity to create helium elements. And that process produces light. It produces energetic light. And that light escapes out from the core and travels through upper layers of the sun until it can finally escape and go through the solar system to us on Earth. Let's follow a photon of light, a photon being the particle of light as it travels through the sun. And these hydrogen atoms, they are made of one proton, one positively charged particle, and one electron, one negatively charged particle. Those four hydrogen atoms are being forced together to create helium and a lot of light with energy. Let's travel a bit further out. We think of the next layer of the sun outside of the core, we call the radiative zone. And so here, particles of light, photons of light, these energetic light particles are moving randomly. Here you can see in this demonstration here, what is a photon of light going to do in the radiative zone? It's going to go randomly in any direction until finally it can escape the radiative zone. Sometimes it goes backwards before it goes forwards. Until it finally makes it out. You can sort of think of this random walk as, imagine a squirrel searching for nuts. It's going to go check by this tree. It's going to go check under that leaf. It's going to double back and check the tree again. Check the tree next to that. It doesn't matter. It will go anyway. It's wherever its fancy takes it. Next, though, after the photon of light has escaped the radiative zone, it enters the convection zone. And here, hot pockets of gas are bubbling and boiling and moving those photons of light and energy out, and up. Think of the convective zone as a lava lamp, these hot pockets of gas rising to the surface. Now, I'm going to turn things over to Mary and Abby for a moment. They're going to walk you through again why the core is important in creating these photons of light, why the radiative zone is able to allow those photons of light to travel outwards, and finally, why the convective zone is able to do the same thing as well. So they're going to introduce you to the core, the radiative zone, and the convection zone a little bit more.
The sun is made out of hydrogen atoms. Hydrogen atoms and all atoms contain electrons and protons. Protons are positively charged, identical charged objects push away from each other or repel each other. This force is called the electromagnetic force. The yellow magnet represents protons. The proton in one hydrogen atom wants to push away from another force, just like we see here. But the strong gravity in the sun, another force, pushes the protons together. Now there's a third type of force called the strong force. When protons get very, very close together, such as the crush of a tremendous gravity like that inside stars like our sun, they suddenly snap together because the strong force causes protons to pull on each other or attract when they are very, very close together. Now watch closely. When these yellow hydrogen protons are subject to a lot of gravity, they snap together, forming a new element. 4 hydrogen protons combine together to make an element called helium. The creation of new elements this way is called fusion, and it occurs when something such as gravity causes the electromagnetic force to be overcome so that the strong force can take over. Fusion is what powers the sun, and fusion in the sun releases photons, or particles or packets of light, an energy that travel out through the rest of the star.
The radiative zone is the next layer above the core of the sun. Here, light photons move around carrying energy, but they don't always move in one direction. They move erratically, going this way and then that way. Eventually, they find their way up and out of the radiative zone, moving their energy to higher up layers of the sun. Here, the bumbleballs represent light photons in the radiative zone. Follow the blue ball with your eyes, and you will see its motion is mostly wind.
The convective zone of the sun is a region of the sun that's above the layers of the core and the radiative zone. It is just below the surface of the sun, which we call the photosphere. This boiling silicon aluminum oil represents the convective zone. In this region, light photons and energy of the sun are carried up from the interior of the sun and out into the outer layers of the sun and out into space in a process called convection, which you can think of as similar to boiling. Great bubbles of material called convection cells rise to the surface of the sun like lava lamps or hot air balloons, carrying light photons and energy outwards into the upper layers of the sun and into the solar system towards Earth and other planets. When we look at the surface of the sun, we can see a molted pattern like we saw here before Abby stirred the boiling oil. We call this pattern appearance granulation. What we're seeing when we look at the surface of the sun and we see this pattern in the convection zone peeking through the surface of the sun, this oil might look like it's sitting still, but it is constantly boiling and transferring energy upwards and outward, like the convection zone in the sun. If we disrupt this pattern like Abby did, it forms again. As you can see, if our camera is good enough, you can see the movement of the oil particles within the convection cell. The convective zone is now constantly moving light photons and energy out into the upper layers of the sun and into space.
Thank you, Abby and Mary, so much. We're going to think above the radiative zone and the convective zone now. But before we do, I'm going to ask you all a question about what we've learned so far about the interior of the sun. Could you please try to remember atoms like hydrogen, what particles are they made of? And let's do about 5 more seconds. Okay, let's see the results. Yeah, y'all got it. Very nice. Very nice. We've been talking a lot about photons when the hydrogen combine, 4 hydrogen combine to create a helium atom, they do release photons. They're not a part of the atom, but it's been something we've been talking a lot about. And so, the photon being an answer was really intuitive as well. But electrons and protons. Now, when we think about above the convective zone, the next layer of the sun, the surface of the sun really, is what we call the photosphere. And there's a special way to look at the sun with a oftentimes solar telescope is going to just be looking at a very specific color that hydrogen gives off, that the sun being made of hydrogen gives off a lot of this one really red color. When we look at the sun with a solar telescope, which is a great safe way to view a partial or total solar eclipse, we do see all these cool features when we're looking at the sun in just this one particular red color of light. We can see little sunspots. We can see a number of other features as well. We see these prominences. These are charged particles traveling along the magnetic field lines of the sun. We see granulation. That's familiar to you guys. It's basically the top of the convective zone peeking through the photosphere. When we view prominences not on the edge of the sun, but right on the main circle that we see, we call this the face of the sun sometimes. When we're looking at prominences right down directly above them, we'll actually see those same arcs, but see them kind of darker there. Call these features filaments. And here's a close-up on a filament there. But what's quite cool is where these prominences, these particles traveling along magnetic field lines, where magnetic field lines enter and leave the sun, this creates a particular phenomenon called a sunspot. We'll come back to that. A sunspot is a cooler region of the sun that's still pretty hot, but it's cooler in comparison to the rest of the photosphere. And so it appears kind of dark. Let's go back and just briefly say, here are some more images of prominences. And sometimes magnetic field lines will break and you'll have this solar flare phenomenon we see here, or a coronal mass ejection, sometimes we call them. But before we transition to, we'll do the activity first. So Abby and Mary are going to take it away again.
First, we'll view a sunspot represented by the light bulb. The sunspot is hot and shines brightly. Then, without turning off the sunspot light bulb, we add the surface of the sun, the photosphere, represented by the overhead projector. Now, the surface of the sun is so much hotter and shines so much more brightly that the sunspot that it causes the sunspot to appear dark in comparison. The sunspot is still hot and bright, but not compared to the surface of the sun. The sunspot light bulb, a slightly cooler zone on the sun, appears dark.
Thank you so much, Abby and Mary. We're going to jump into our third question related to sunspots. Could you please answer, what is a sunspot? All right, a couple more seconds. Okay, let's see the answers. Yeah, very nice. Very nice. And I like what you're saying, extremely hot zones on the sun surface. I don't think that's wrong. Perhaps maybe I didn't write this question as well as I should have. I like extremely hot zones on the sun surface, but they're kind of cool. They do have strong magnetic fields. I think I'll take 3 or 4 for the answer here. So now that we know a little bit more about how the sun moves energy out beyond its layers and into outer space so that it can travel to Earth, we know a little bit more about how the sun works. Let's go back to the main reason why we're here today, which is to talk about solar eclipses. So what's going to happen if you go to the path of totality? What's quite cool is it gets incredibly dark. There's also this phenomenon right before the moon completely blocks the sun, where just a little bit of the brightest regions of the sun are still able to be seen. These features, known as a diamond ring or Bailey's beads, appear right before the total corona pops out, or also right after the corona is done shining and the moon is starting to pull away from perfectly blocking the sun. Then there's also this fantastic sunset appearance that is all around you in every direction. This is basically because just as when the regular sun sets, there is a region beyond you that can still see the sun. That's true during an eclipse. In every direction, there's a region beyond you, a portion of the earth beyond you that can still see the sun. When the regular sun sets, you are mostly in a darkened sky, but there's still a little bit of the sun on the horizon. And in fact, the sunlight is bending through all these thick layers of the Earth's atmosphere, and so it makes it look particularly red when the sun sets. The same thing happens during a total solar eclipse. You're completely in dark, but it's not too far away in every direction that the sunlight still shines. And you can see that sunlight traveling to you, skimming along the surface of the Earth through lots of atmosphere that turns it that sunset red color. Amazingly, when the moon blocks the sky, you can actually see the brightest planets and the brightest stars that will again be visible when the sun sets that evening, but the sun is still up. It's just blocked by the moon. And for example, right now, Jupiter is very bright in the sky. Also, the star Sirius, the dog star in Canis Major, is very bright right now. And so if you're in the path of totality, when the moon blocks the sun, try to see if you can see Jupiter or Sirius. And then also, birds stop chirping. It's become so dark that they think it must be nighttime. Crickets, frogs might begin to make their nighttime sounds because, again, the whole Earth, from their perspective, seems to have darkened like nighttime. So hopefully you'll be able to catch this eclipse, but we're due for another one in about 20 years, which will be quite cool. That's going to be in 2045. In 2045, we'll have another great North American eclipse. Here's another eclipse that will occur the year before the next total solar eclipse in the continental US is going to be 1 year before this great North American eclipse, but it's really only going to catch parts of North Dakota and such. Like we've said before, there are about 2, sometimes even 3 or 4 eclipses every year when the sun The moon and the earth are in that nice straight alignment. But sometimes those eclipses are just partial eclipses. It's only a portion of the moon's shadow that's falling on the earth. And it's really only maybe every year and a half or so that we get to have a total solar eclipse here on Earth. But that's always at a very particular place on Earth, and you might not be there. And so wherever you live, wherever you go to school or go to work, that place is only going to see a total solar eclipse every like 400, 300, 500 years, incredibly. Now, of course, we had a total solar eclipse in North America in 2017, as many folks may remember. But before that, the last total solar eclipse in North America that stretched across all of North America was in 1918. So I feel pretty grateful that, we'll have another great North American eclipse in just 20 years. And I'm really looking forward to the one on April 8th. Now, as we've said before, it's very common for eclipses to happen in the solar system. Moons are always blocking the sun. That's not uncommon. Sometimes planets block the sun. It's possible to see Mercury or Venus eclipse the sun. Here is a moon of Mars passing in front of the sun, viewed from the perspective of the rover on Mars. We're seeing an eclipse of the sun by a Martian moon here. But what's incredible, of course, again, about our eclipses here on Earth is that our moon appears so close to the size of the sun in the sky. So we've got this perfect, nice, perfect blocking of the sun. Now, kind of one fun thing is a lot of folks might like to think that every astronomer is so excited about the eclipse because of all the things that we can study. The average astronomer is actually just excited about eclipses for the same reasons that you're excited about eclipses. It's just so cool to see this happen. But that's not to say that there's no research or no science that can be done during a total solar eclipse. It is possible to study that outer atmosphere of the sun, what we call the solar corona. We designed telescopes that can block the sun so you can see the solar corona, but the moon does it for us every couple of years. And so it's a great opportunity for that. And then, of course, there are kind of effects that happen to the Earth just because we've got this sudden temperature drop at an irregular time. There are effects of the eclipse on the atmosphere of the Earth, which we can study. And another way that total solar eclipses can be useful for research are to think about these models that we make of how the sun works, how much energy it transfers, what its magnetic field looks like, all these simulations of how we believe the sun behaves. We can, in our software, simulate what should a corona of the sun look like if the moon were to block it tomorrow. What is the corona doing today? And we can run those models and we can make a computer prediction of how the corona of the sun should appear. And we got this picture of the corona by really understanding and trying to predict the correct physics that goes on within the sun. And on the day of a total solar eclipse, you can take your model and you can compare it to the actual observation of the corona. And you can see, do I understand how the sun works well? And if so, my simulated corona will look just like the observed corona. I do want to share with you a couple of ways to stay safe during the total solar eclipse. It can be very damaging to look at the sun. So always wear eye protection when you're in the partial phase of the eclipse, when the penumbra is falling on you. There's really just a couple minutes for total solar eclipses where it's safe to remove your glasses. Then also make sure that the solar eclipse glasses that you have are still good. They weren't in your pocket and got damaged or ripped or a hole poked into them by your keyring. Of course, regular sunglasses are not good protection. And any sort of camera, binocular, telescope that's looking at the sun, it needs to have a high quality solar filter on it. And solar eclipse glasses, while they're safe to use on your face, you should never use solar eclipse glasses with binoculars or with a telescope. Those should never be combined. May I have you guys check out this fourth question here? All right, 2 more seconds. Let's get those results. Well done, guys. So there are some cool tools for looking at the sun on eclipse day. Something like a welder's helmet behaves like safe solar eclipse glasses. A kitchen colander, holes punched in metal, circular holes, are going to, when you hold them up by the sidewalk, make a little picture of the circular sun when the eclipse is not going on. But during the eclipse, as it's approaching totality, or if you're just in a partial eclipse area, you'll see those little crescent shapes, those little phases of the sun on the sidewalk instead of those perfect circles images of the sun you would see if there weren't an eclipse. Just like this colander behaves as what we call a pinhole camera, leaves on trees, their shadows are also creating images of the sun, behaving like a pinhole camera. So these little circles you see here are images of the sun, and this is just on an ordinary day. Whereas during the partial solar eclipse, or as the total solar eclipse is approaching totality or leaving totality, those little leaf circles, leaf shadows become a little crescent sun. Of course, there's a lot of different ways to think about the importance of eclipses. Norse mythology, Javanese mythology. For Navajo people, it's often quite common to choose to not even view the sun out of respect for it at the time of an eclipse. And the Kukwatl people of Canada believe that, in their mythology, something's swallowing the moon. Let's quickly remember some of the things that we've discussed. Oops.
Total solar represents you. Our okay, so we have our sun, we have our moon, and no Earth, because you're the Earth. Okay, your camera angle that you're looking through right now represents you looking out into the sky, looking at space, and looking at the sun. So a total solar eclipse is when the moon, which orbits the Earth, orbits you about once every month, when the moon happens to line up exactly with the sun, which, considering the two things aren't anywhere near the same size, is sort of amazing. But your camera angle helps us explain why. In reality, the sun is about 400 times bigger than our moon, but by sheer dumb cosmic luck, it's also about 400 times farther away. So in our sky, they can appear to be the same size. I mean, that's the whole joke with that old Kids in the Hall head-crushing skit. I pity you and I crush you. Sorry, nothing personal. I mean political. Okay, you can stop that. But then why don't we have total eclipses every month if that's how often the moon comes between us and the sun? Well, because the moon's orbit is not always perfectly aligned with the Earth and the sun all the time at the same time. It's a bit angled. So imagine in some random month, the moon could be orbiting the Earth in its off angle axis. And when it comes directly between us and the sun, it might actually be here. So it's not actually blocking the sun at all. Or maybe we only get a partial eclipse, which is when the moon passes over the sun, but never quite completely covers it up. Or sometimes, because the orbit is an oval, it's not a perfect circle, meaning sometimes the moon is farther away from us than normal. It actually appears smaller in the sky than the sun. We call that an annular eclipse, or maybe you've heard of the Ring of Fire eclipse. Same thing. But the moon casting a shadow on the Earth in such a precise way so that the sun and the moon are exactly the same size in the sky and they overlap exactly one on top of the other. That only happens once every 1 or 2 years. And for you and me specifically, depending on where you live, April 8th might be even more special than that. Total.
Okay. If you happen to be anywhere near to Iowa City on April 8th, we invite you to the University of Iowa Pentacrest, East Pentacrest, and the Sciences Library Courtyard. We'll be having our partial solar eclipse event there and then. As you all get excited for the eclipse in your own locations, I want to ask you a final question. What are you looking forward to? Now, some of these events are only possible if you're in the path of totality, but towards the bottom of the list, there's some things that can be seen even if you're experiencing that partial eclipse. Couple more seconds. Okay, let's see the answers. Nice. Cool. I love it. Some good spread between, what can be seen at partial locations and what's only possible to see during totality. Then, of course, if you ever find yourself near Iowa City, I do also want to invite you to the Department of Physics and Astronomy has a number of public observing events. For this spring, this is our 3rd public observing for the eclipse, but we do have a public observing night coming up on April 26th. It's a Friday night, 8 to 10 p.m. And we'd love to see you there also if you ever find yourself in that part of the country. Visiting your alma mater or your student's school. Finally, I just want to share a little video that every time I watch it gets me so excited for what's coming up on Monday. Let's check this out before we say goodnight. This is the 2017.
August 21st, 2017. It's in a lifetime thing for them. A lot of people. This is going to see something like this. Here in New York, we get about 71% coverage. It's going to be totally cool to see. 200 million Americans live within a day's drive of what's called the path of totality. About 60,000 people are expected to travel here, nearly tripling the size of the city. But they are expecting 100,000 visitors to watch the eclipse.
Eclipses occur, total eclipses, every 2 years. But having this one going from the Pacific Ocean to the Atlantic Ocean across the world's 3rd most populous country is a very unusual event. You just want to be part of this thing that happens once every 375 years. It's a shared moment
And spaced out here. The moon is starting to cover the sun. Totally vibes right now. Just vibe out with me right now.
So much energy. I've been waiting for this for like ever.
Yeah, just a normal work day. Yeah, I mean, I didn't really trip out, but I didn't think it was going to be that much, you know. Why you just get dark out of nowhere? Like, what the heck is that? You know, you just got to step back and you just got to think to yourself, like, man, that's beautiful.
We're observers here. This is nature's event. We are really witnessing like this incredible, majestic choreography of orbital mechanics. So I think it's a really important time to reflect on our place in the universe.
It doesn't feel like a big disappointment that it rained. It was so cleansing, actually. I mean, people ran up and said, "Do you want to use our glasses?" You know, and so we got to see it through glasses too.
That's an impressive sight. There it comes. A little bit.
Stop. Almost.
Oh my God.
Oh, look at that. Look at the skyline. It looks like night.
It was amazing. Like you stop
When that diamond ring came out,
it kind of felt like love.
heard little crickets come out chirping and all that because it got dark, and I don't know, and I felt the temperatures drop.
Celestial things are just beyond comprehension. And when you see one and it's really there, and we're all here.
Everywhere.
I bet the whole world was looking up. I bet the whole world was looking up.
Well, I am so excited for Monday, and I know you guys are too. I want to say thank you, Lynn. Thank you, Tegan. Thank you, Mary. And thank you, Abby. And thank you especially to each of you for being here tonight.
Excellent. Caroline, thank you so much, and to Abby and Mary as well for sharing all of that incredible information. We did have some questions come in, so I want to be sure we take a moment to address some of those. And you touched on a little bit of this, but I'm going to tee up some questions to you to make sure that we do cover all of them. So the first one that came in, you touched on how ancient people reacted to eclipses, but when did astronomers start to figure it out?
Oh, what a good question. I think even, the Greeks and Romans were able to use eclipses to determine properties like what is the size of the moon and what is the size of the earth. So I certainly want to say very early in our history. I don't know an exact date, unfortunately.
Okay, very good. Thank you. Another question came in from David. Is it just a coincidence that the sun is about 400 times bigger than the moon and about 400 times farther away from Earth than the moon, or is some physics principle involved?
Oh, very good question. I would say that it is a coincidence in terms of we don't see these sorts of things happening with other planets and other moons in our solar system. If it were related to physics, we would see happenings like that more commonly in our solar system. But yes, certainly likely a coincidence, from a pure scientific perspective. And then you yourself can decide if there's perhaps some other significance there, but certainly scientifically a coincidence.
Great, thank you. Another question, Norma asked, is it possible for the sun's energy to be depleted as it releases energy to the atmosphere?
Ooh, yes. So eventually the sun will run out of the ability to create energy. It's not because the atmosphere is taking that energy away per se. It's just that there's only so much hydrogen in the sun. And so the gravity of the sun is going to continue to crush it down. And eventually there will be a point where there's no more hydrogen in the core that can be fused into helium. And the sun will start to fuse helium in the outer regions a little bit more rather than just in the core. And the sun will expand. And after a while, it will even lose the ability to do that. But the sun will eventually run out of the ability to create energy.
Okay, thank you. We had another question here from Jeannie asked, if even if it's cloudy, will we still be able to see any portion of the eclipse?
It depends on how cloudy it is. So, you were able to see in that last video there, they kind of had scattered showers and scattered sunlight. They were able to see even through enough clouds that it was raining a little bit. They were able to have the sun peeking through that they were still able to enjoy the eclipse. And so if those clouds are moving, if we're, popping in and out between the sun's clouded over and the sun is visible, then it's certainly possible to enjoy the eclipse still, especially during that nice long multiple hour partial eclipse experience. If there's a coverage of the sun during the couple of minutes of totality, that could hamper the experience a little bit, but it's still possible to see totality and go back and forth between some clouds passing. It's really about how thick are the clouds? Are they moving? Are you able to see any sunlight peeking through at all?
Excellent, thank you. Another question came in here from Ginny. I've never heard of 380 degrees. How is that different than 360 degrees full circle?
Ooh, there you go. You got me. It's a typo on my part.
Oh,
yeah.
Okay.
360 is the one. 360 degree sunset.
360. Now we know. Thank you, Jenny, for that call out.
Thank you.
And then we had several questions come in actually regarding safety when viewing the eclipse. So I do want to touch on these as it's very important as you
for sure.
discussed. So should we be worried about eye damage? I know you talked about that a little bit already, but a couple more questions that came in. Is it safe to wear Eclipse sunglasses over your own prescription glasses?
That would be fine. That is safe to use them in conjunction with your own prescribed glasses.
Okay, great. Will pets that are outside during this time be safe and not damage their eyes?
Ooh, very good question. Your pet, it has an ability to kind of know to protect itself, sort of thing. So it's not going to be like really staring up in the sun, like in that direction around that time of day anyway. If your pet is just kind of, going about its day sort of thing, it's not likely to look in that direction or be shocked enough to look in that direction. So your pet would be safe. It did look like there were some people in some of the videos with little special glasses for their dogs, but I think that's a fun thing to do and not a requirement for pet safety. I feel like there was another safety question in there I missed.
There was another one. What type of damage does the eclipse do to our eyes / retina?
So it's important to note that the damage that an eclipse could do is no different from just the regular damage that looking at the sun right now, ordinary day, no eclipse. If I were to go out and look at the sun, that would hurt my eyes as well. And it would hurt my eyes in a similar way that the eclipse would hurt my eyes. And it's just because we don't usually look at the sun. We know it's safe, to look away from it. But if we look directly at the sun, that's a bad decision. So we're going to be, looking at the eclipse, looking at the totality, and then suddenly after a couple minutes have passed, you'll start to notice that it's maybe getting a little lighter. You want to quickly put those glasses back on. It's really not that there's any huge risk beyond just usually looking in the direction of the sun is a bad idea. You want to, wait until people around you, perhaps you're in a group of people, have said, oh, we're in the path of totality now. You're going to, see darkness all around you. For a few seconds, a few minutes, it's safe to look at the sun if you would like. And then after you've enjoyed it, a little time has passed, just put those eclipse glasses back on for safety. There's, leading up to totality, there's nothing more risky about the sun at the time of an eclipse or anything like that. It's just that you're looking towards the sun when you normally wouldn't. And so that just kind of adds a little bit of a risk factor there, but it's no more dangerous than the regular sun. I still feel like there was a couple questions a couple minutes back that I failed to answer. I'm trying to remember what they were, but I'm sorry if I skipped over your question.
That's okay, Caroline. You're doing great. Laura did ask another one. Why shouldn't you combine solar glasses and binoculars?
So if you are certain that you are completely covering the entire lens of the binocular, it is possible to buy safe attachments for the front of your binoculars, but it's very important to know that the protection always needs to go on the side towards the sun. You would never want to have any sort of protection near your eyes with device protection eyes. That's very dangerous. It would always need to be protection, device, and then eyes. So if you have specialized binocular adapters, solar grade solar filters that you're putting on the front of your binoculars, that would be fine. I can even share, a link for safe vendors of those products with Lynn and Tegan to distribute with you all. But the real thing is, with the solar eclipse glasses pair, you just can't be certain that you're really blocking the binoculars completely, that you're not accidentally letting a little bit of sunlight come through, or maybe your hand jostles accidentally and a little bit of sunlight comes through into those binoculars. That's the reason why you don't want to use them in conjunction. One, they just don't affix very well to the front, and it's too easy to get confused and accidentally put them on close to your eye rather than on the far end as they need to be. And I will say there was that question about glasses, and I failed to say, glasses where you want to put the eclipse glasses on top of your glasses. You don't want them to be under your glasses and your glasses go on top. You want to wear your glasses like normal and then put the eclipse glasses above on top of them. Okay. Between you and your glasses, the eclipse glasses are between you and your glasses and the sun.
Fantastic. Well, the safety is the most important part of this. Of course, we all want to get out and enjoy it, but doing so safely is the priority.
Absolutely.
Very good. That is all the questions that I saw through that Q&A function. And I know that we are over our hour. We had such fantastic information shared with us and really great questions. So thank you everyone for sharing those. And it was a great discussion, Caroline. So we appreciate everything that you shared with us as well today. In closing, wanted to thank everyone again for joining us this evening, for Caroline, Abby, and Mary sharing your expertise, and for everyone asking those great questions. If we did not address your question, please know that we are sending out a follow-up email after our time together this evening. So keep an eye out for that. You'll be able to contact us with any questions that we were not able to address this evening. And then, of course, we are all looking forward to next Monday, April 8th, to enjoy the eclipse. I know I have my glasses ready to safely enjoy that. So we will look forward to that. And then, of course, if you are looking for more opportunities to get involved, attend events, or just for any other opportunities to take advantage of, you can visit www.foriowa.org. So again, Caroline, thank you so much for your time this evening. Thank you, everyone, for joining us. With that, have a great evening.